Welcome back. My name is Arturo Sanchez, a mechanical engineering student, and I'm under the guidance of Dr. Daniel Benuti at the University of New Mexico. This is part 2 of the ME317L Fluid Mechanics Slip and Slide project, where I will be presenting my analysis of the results and breaking down all the calculations. The intention of this experiment was to validate and verify Newton's law of viscosity. To reiterate, Newton's law of viscosity is a relationship between the shear stress, viscosity of a fluid, and the velocity gradient. The shear stress occurs at the boundary layer in a Newtonian fluid and acts contrary to the force being applied to it. The fluid will deform continuously, and the plate where the force is acting will travel with the same velocity as the fluid. This figure shows an exaggerated view of the system that will be analyzed in this project. Notice that the boundary layers are thin and parallel and move in a laminar flow. At the surface area, where y1 and u1 are located, the velocity here is assumed to be 0 because of the no-slip condition. At the boundary layer, where the surface of the water and the plate meet at y2, right here, the plate is acted on by a driving force P. That force causes the mass plate to move from position 1 to position 2 with some velocity. The gradient is created and assumed to be constant in Newtonian fluid and thus has a linear rate of change. This is the gradient right here, the rate of change. The slope of that gradient is the viscosity of the fluid. Proof of validation. To validate and verify Newton's law of viscosity, the empirical data collected from the experiment will be used to calculate the viscosity, the Greek letter mu. Viscosity of Newtonian fluid, such as water, is a fluid property that is well known and easily accessible in any source. Using table B2 from the Fundamentals of Fluid Mechanics textbook, we can validate the experiment by obtaining the value of mu, viscosity, which is 1.002 times 10 to the negative 3 Newton seconds per meter squared at a temperature of 68 degrees, which is equivalent to 20 degrees Celsius. A recap of the experiment. The assumptions here were that there was steady and incompressible flow, no outside forces are acting on the system, the study was conducted with laminar flow only, the velocity gradient generated by the driving force, du over dy, is assumed to be constant. If you haven't seen part 1 of this project, I encourage you to visit the link that I have also posted in the comments. There you can see the experiment and recreate it for yourself. But since you're already here, I'll briefly recap the experiment for you here. To summarize, the driving force P is applied to the plate, which sets the plate in motion and causes a shear stress to act on the boundary layer between the plate and the surface of the water by applying a contrary dampening force to the motion of the plate. These shear resistive forces acting on the plate conform to Newton's law of viscosity. This procedure began with a driving force that was my arm sliding a mass weight across the dry surface. The purpose of that run was to gather data to quantify the initial driving force. Then another trial was conducted under the same conditions, except 54 fluid ounces was poured along the channel and viscosity was introduced. Relevant data such as temperature, displacement, velocity, and time were collected during these trials. Here's the disclaimer. Don't try this at home. Just kidding. I encourage you to try this at home, but seriously. Before conducting this analysis, it's important to mention that I greatly underestimated the complexity of validating this seemingly simple relationship. During initial analysis, the law of viscosity became difficult to comprehend when flow rates were introduced into the system. Introducing flow rates complicated the analysis because there were now two forces applying an acceleration on the plate. I attempted to uncover a detailed procedure of Newton's 17th century experiment, but unfortunately, I couldn't find a single reference. It's likely that Newton conducted this experiment using a static body of water in a closed container to make the calculation easier. This simplification allowed the analyst to omit many of the extraneous factors and greatly reduce errors that would have been introduced through approximations. There were some difficulties and many assumptions and simplifications that had to be made to verify this law. Thus, I found it practical to omit the third and fourth trials from this analysis because of their complexity and extraneous forces that were introduced during the experiment. I'd like to take a moment to describe what could have been done better. A note for future scientists who wish to reproduce this experiment: it is important to mention some changes that should be applied to the mass flow trials. Number one, the mass plate needs to be heavy enough to cause a shear stress, but light enough not to disrupt several boundary layers. If it's too heavy, it will introduce extra resistive forces, making it difficult to quantify those forces and calculate the viscosity. The distance between the layers needs to be constant and not disrupted. Basically, it needs to have laminar flow. In this experiment, during trials 3 and 4 where a mass flow rate was introduced, the mass weight was too heavy and it increased the resistive forces causing turbulent flow and added pressures into the equation. This is why those trials are omitted from numerical analysis. Also, the force that was applied to the plate was too intense to keep the boundary layers as thin parallel layers tangent to the velocity vector. This was made apparent when the low flow rate trial had a displacement that was less than the static flow trial. Also, water could be seen leaving the system in the y direction, suggesting that an acceleration was occurring in the y direction. It also indicated that flow was not completely laminar and was resisted by many more forces than shear stress alone. Had this been done correctly, the low and high flow trials would have been smoother, and both the velocity and displacement should have been much greater than the dry and static flow trials. The omission of trials 3 and 4 during analysis. Due to those reasons, an analysis on trials 3 and 4 where mass flow rate was introduced will not be conducted. The analysis will solely focus on the dry and static flows. Calculations. With all that out of the way, let's proceed to the fun stuff, the calculations. First, we begin by gathering all our known parameters. The method for validation will be to use Newton's relationship between the shear stress, viscosity, and velocity gradient, and break each of these terms down into parameters that we can either derive, measure, or calculate. For instance, we have the shear stress, which we know is defined as a force per unit area. The area we know because it is the area where the fluid is in contact with the surface. We know that the velocity gradient is constant, and du over dy can be approximated as u over y, which is the velocity over the height. The velocities were measured from the experimental data, and the height or thickness of the boundary layer can be determined from other known parameters in the experiment, such as the area and the volume of the channel. We are using the viscosity itself as a known tabulated parameter, and it is the mechanism being used to verify the law of viscosity. We need to determine a few more parameters such as a driving force, acceleration in the x direction of the plate, and the height of the boundary layer. Let's begin. The purpose of the dry run was to calculate the initial driving force applied to the plate for use in the static fluid body trial. The method for finding the driving force P will be using Newton's second axiom, where force equals the mass times the acceleration. Since we're using classical Newtonian mechanics, we need a free body diagram. Luckily, we have one right here. Using classical Newtonian mechanics, we can use this free body diagram. We can determine the forces acting on the plate. This also operates under the assumption that the only force acting on the plate in the x direction is the pushing force I applied to set the plate in motion and the force of the friction that opposes the applied force. The figure shows the forces acting on the plate in a dry no-flow trial. The force of friction moves contrary to the driving force in the x direction, and a normal and gravitational force act on the plate in the y direction. Calculating the acceleration of the plate. Since there was an acceleration that occurred in the x direction of the force I applied, the acceleration needed to be calculated. We know the acceleration is the rate of change of the velocity, so we use this equation right here. The final velocity was assumed to be at rest. The initial velocity was measured and recorded as 0.3984 meters per second, and the time it took to come to rest is 2.46 seconds. Plugging all these into our equation, and we get the acceleration of the plate is negative 0.1619 meters per second squared. The negative denotes a deceleration, which we would expect because it is slowing down. One of the forces that we're going to have to calculate is the friction. From classical mechanics, we know that the force of friction is calculated by multiplying the normal force by the coefficient of kinetic friction. I decided to look up the coefficient of friction between plastic and metal, and to be honest, it was a little hand wavy here. There was such a huge range between the coefficient of kinetic and static friction that I decided to just use the intersection of the two to achieve a reasonable result. I want you to notice the large range of values between each of the coefficients. Due to the uncertainty of the coefficient of kinetic and static friction from the source, I decided it was best to use the intersection of the two ranges to provide the most probable coefficient, which was 0.25. Now that we have determined some of the unknowns, we can apply our knowledge of classical mechanics and begin summing forces. By Newton's second axiom, we can determine the initial driving force that is applied to the plate, which sets it in motion. Here. Let's begin by summing forces in the y direction. There's no acceleration in the y direction, and this simplifies to a statics problem. The only force acting on the plate are the normal and gravitational accelerational forces. We know these values. Putting these into our equation, we can calculate the normal force, and the value of the normal force is 4.905 newtons. Now let's look at the right side, where the forces will sum are in the x direction. The forces acting on the plate in the x direction are the driving force, P, the force of friction, and it has an acceleration which we already determined earlier. Solving for P, the applied force, we get P equals the force of friction plus the mass times the acceleration. In the next line, the force of friction is expanded to its definition. And now we have all our parameters right here, which we can plug them into our equation and determine the driving force, P, which is determined to be about 1.1453 newtons of force. It's important to note that the initial force acting on the plate P is assumed to be constant throughout all the trials and is close enough to be approximated as such. Another parameter that we need to determine is the height parameter of the channel. I did not measure this with a depth gauge, and a ruler could have been used but wasn't. However, we know the area and that the static body of water covered in the channel, and we know that the volume of the water in the channel, so we can determine the height from those relations. We'll find the height of the channel in the static flow situation. We're going to let y be equal to the height. Thus, and we know the volume and area of the channel. Thus, the height y of the water in the channel can be determined by dividing the volume by the channel by the area of the channel. And the height of the water, so we do some calculations here. We plug it in and we get the height or the thickness of our boundary layer, and it's 3.5261 millimeters. Since the velocity gradient is assumed to be constant, dy can be approximated as delta y. To make calculations easy, let's set the initial y value to be the surface layer and starts at 0. So delta y is just y, and we end up with the same value right here. The velocity was calculated and tabulated from the results, and since we are applying our calculations in a static flow, we use the velocity of water and the plate from the second trial, which is 0.7702 meters per second. Applying the same logic we did for the height of the water, where the velocity gradient is assumed to be constant and du is approximately delta u, which is just u, we get this value right here. All the unknown parameters have now been determined, and we can apply them to the relationship defined by Newton's law of viscosity and validate it. At the top, we start off with the law of viscosity, which we started with. We use the definition of shear stress to be the driving force divided by the area. The driving force of the plate is given right here. The area of the plate applied to the surface of the fluid at the boundary layer is given right here. The change in velocity at the boundary layer is given right here. The distance between the surface layer and the surface of the plate is given right here. Rearranging the equation and solving for the viscosity, we plug in all our known parameters that we had gotten from all our calculations back there, and we get a value of 0.9794 Newton seconds per meter squared. This figure shows a zoomed in view with all the parameters and shows the parameters of the experiment. A unit analysis confirms that this is correct. This is consistent with the value of viscosity found in table B2 from the fundamentals of fluid mechanics, where mu is 1.002 times 10 to the negative 3 Newton seconds per meter squared. Although there is an error by a magnitude of 1,000, it can be assumed that the driving force wasn't as intense as initially calculated. There could have been an error in the magnitude any one of the parameters. However, the driving force is the only parameter where there was a high degree of uncertainty. Assuming that this is the case and neglecting the order of magnitude error, the error in this experiment is 2.26%, which is good enough for engineering. Thank you for taking the time to review my experiment. This is the end of my analysis. Below is a list of references that I used to conduct my analysis. Thank you.